Now we look at range trees in higher dimensions. So the previous solution easily generalizes to higher dimension as well. But there is another way to look at range trees, and this way we can actually use any data structure that answers orthogonal range reporting or searching queries in d dimensions to a data structure that answers them in d+1 dimensions. So assume we have a data structure AD that uses SD space and QD query time and can answer d-dimensional queries. We like to extend this to dimension d+1. We can do this in the following way. Consider a set of points P. We split them into two subsets of roughly equal size using a hyperplane that is perpendicular to the d+1 dimension. So imagine this dimension is d+1 dimension, and we're using a hyperplane that is perpendicular to this dimension. So we have points P2 on one side of this hyperplane and points P1 on the other side. Then what we do is that we take one of these point sets, we project them onto this hyperplane H. So now these projected points live on the d-dimensional space because this hyperplane H is d-dimensional. Then we store these d-dimensional point sets in a data structure AD that we know how to build. Then we do the same thing for the other one. And finally we recurse on P1 and P2. In other words, we'll be calling the same procedure on P1 and P2. Let's quickly look at the space analysis of this data structure. So imagine SD+1 of n is the space used by this data structure and the point set that has endpoints. Step 1 doesn't use any space. Let's look at step 2. For doing step 2, we project half of the points on a d-dimensional space and then we store them in data structure AD that by assumption uses SD of n/2 space. So and then we do the same for the other one, so we'll have 2 times SD of n/2 space used for lines 2 and 3. And finally step 4 is a recursion, so we'll have 2 times, because we're recursion twice, of SD+1 of n/2 because P1 and P2 have size n/2. These constant factors do not matter inside O notation, so we can just get rid of them. So we can write this as O of SD of n plus this recursion. And if you look at this recursion, then you'll see that this solves to just SD of n times log n. You could see that either using master theorem or just by expanding the recursion tree for this recursion. So the recursion tree will be a balanced binary tree of size of height log n, and at every level of this balanced binary tree you'll be paying at most SD of n space, and since you have log n levels, then you get log n times SD of n space for the whole recursion tree. So the space is easy to analyze. Now let's look at a query. So imagine we have a query box query box Q. I would like to answer we want to answer the query for this box. Either count the number of points inside or report the number of points, list the points inside this query Q. We have 2 easy cases. If query Q is completed to one side of H, then we can recurse only on one of points P1 and P2 or P2. For example, if query box is complete to the right of this dividing line, then we only need to recurse on P1 because it can no longer contain any points from P2. And the same holds if the box is complete to the left. So the interesting case is when this box intersects this hyperplane H. If that's the case, then we can write this query box as the Cartesian product of this rectangle Q prime, that is the intersection of H and the query, times an interval L and R. So L is the left endpoint of this interval and R is the right endpoint of this interval. In this case, you can observe that the query decomposes to 2 d+1 dimensional queries. However, these queries are unbounded in one side, so they have 1 fewer boundaries. In other words, we could call a secondary query procedure that is query unbounded from left on the query region that is defined by Cartesian product of Q prime times this unbounded interval. And we call this query on P1, and we do the same on P2. So we call a query that is unbounded from right and Q prime times L to plus infinity. Yeah? and then we'll show that these queries can be answered efficiently. Since these queries are similar, we only focus on one of them. The other one is essentially identical. So let's look at query that is unbounded from left. Assume this query has been called on points at P. And again, this points at P, since we have a recursive data structure, this has been decomposed into 2 points P1, P2 using a hyperplane H. In this case, we have one easy case. If query Q is completely to the left of this dividing line, then we only recurse on P2. Observe that this query cannot be to the right of, completely to the right of this dividing hyperplane, because it goes to the infinity, or it goes to the minus infinity from this side. So the other case is when the query intersects the hyperplane. In this case, I could write the query as, again, Q prime times this interval minus infinity up to R. To answer this query on the right side of this hyperplane, I can just use the same procedure, so recurse on the right side. So I will be calling the same unbounded from left, Q prime times minus infinity times R. But the part of the query that is on the left of this dividing line is actually easier, because this is equivalent to answering a d-dimensional data structure query. Remember that we have projected all the points on P2 onto this hyperplane, and we have built a d-dimensional data structure. Observe that if I find the number or the list of points of the projected points that are inside the query Q prime, then I have answered the query that is inside this unbounded query with respect to P2. So I just need to query Q prime on the projection of point P2 on L, and I have built a data structure for this. So this is the procedure to answer the queries that are unbounded from left. As I said, to answer queries unbounded from right, it's going to be very similar. Okay, let's analyze this. The interesting case is when query the d plus 1 dimensional query decomposes into two unbounded queries. So if I go back here, case 1 in the when you answer d plus 1 dimensional query is uninteresting, because you just recurse without doing any action, or you just spend constant time and you recurse on a point that is half the size. So this is actually a cheap step. The interesting part is the else step. But when this else step happens, then you no longer are going to call the query of d plus 1 dimensional query anymore. So I could write that the query time that it takes for d plus 1 dimensional query is essentially 2 times that it takes for an unbounded query. So now it remains to analyze the query time of unbounded query. If you look at this recursion, again, step 2 is easy, because you just recurse on a point that is half the size by spending constant time. So the time consuming step or case is when else case happens. So in this case, we first recurse on a point set that has half the size. So we have this recursion, plus we call the d-dimensional query on a point set that is half the size. So then that is bounded by this function. If you look at this function, this solves to log n times query time over d-dimensional space. This is in fact a slight overestimation, but this overestimate this recursion only by a constant factor. To see why this recursion solves to log n times q of d, you can just expand this recursion. So this will expand to q of d of n plus qd of n half plus n over 4 plus n over 8 and so on. So you'll have log n terms of qd, and all of them are smaller than qd of n, so therefore their sum is at most log n times qd of n. So to summarize, with these range trees, if I have a data structure with this much space and this much query time, I can get a d plus 1 dimensional data structure where these parameters are increased by log n factor. I can plug this in using the results that I know. So I know that in one dimension, using a balanced binary search tree, I can have linear space and log n query time. And if I keep using this range trees, I will get that in d-dimensional space, my query time is n times log to the d minus 1 of n, and the query time is log to the d of n.